Our topic for the next little while is going to be integer linear programming, which is going to be sort of, obviously connected to linear programming, but it's also going to connect linear programming to a lot of other things we've talked about in the module. Okay, so, and that's something I think I've hinted at a few times, right? That a lot of things we're doing are sort of related to linear programming, and hopefully this week that'll kind of it'll become more clear what's the connection between things like matchings and things like that and linear programming. So remember, this was quite a long time ago now, 6 weeks ago or so, but we were talking about linear programming at some point, right? So a linear program is a problem where you want to, where you want to maximize or minimize. So I'll just say maximize, but also it works for minimize a linear function in n variables over some sort of linear constraints, right? Right. So linear programs basically looked like this. You take, for example, you want to maximize some sort of sum where it's like ci xi, I from 1 to n, subject to, so the xi's are the variables, right? Ci, these are just some real numbers, right? And then you have some constraints like this, so a1i xi, and you have like m of these constraints. So, and this is at most, let's say, b1, this one's at most, say, bm. And in between, like you have, so for each kind of first index here, I have another constraint, right? You have m constraints. These are real numbers. These things, let's say, ji, are also real numbers. And then your b, j are just a bunch of real numbers. Like you just have all these kind of linear constraints. You want to maximize a linear function, right? So this should be review. And the way we wrote this was like this is a kind of cumbersome way of writing this, right? So we usually wrote this in matrix form. So in other words, we wrote it like this. So maximize some vector C transpose times x. So where x is just the column vector x1 up to xn, subject to some constraint ax at most b, where A is the matrix that contains these aij's, and B is the vector which has the bi's or the bj's in a column, right? Where, so this notation meant that so vector, if you have two vectors and you say that this one's at most this one, so this just means that every coordinate of y is at most the corresponding coordinate of z, right? Coordinate-wise. Okay, so that's just a review of what linear programs were. This is something we spent a whole week on, right? But so what's an integer linear program? So it's almost the same thing. So an integer linear program, and sometimes so ILP, or sometimes I might just say integer program, right? So so just sometimes just an integer program. We're always going to be looking at things that are linear, so sometimes I might not say the word linear by mistake. So it's the same sort of thing. So there's a problem of the form. So it's the same as before. You take some linear objective function. You have some linear constraints. And then you have one more constraint, which makes it different, that your variables have to be integers. Okay, so before, right, we were dealing with these variables were always kind of any real numbers, these x1 up to xn, and now I'm saying so in other words, xi is an integer, right, for all I. So you're only allowed to use integers. Is it clear what the basic problem is? Okay, so let me give you an example of a kind of general type of integer linear program, which will connect this topic back to some of the other things that we've been doing. Right? So actually, pretty much every problem, I don't know if I can maybe even say every problem we've looked at in this module can be phrased in some way or another as an integer linear program. Okay, so for example, if we look at matching, right? So let G be a graph. And consider the integer linear program. So the following integer linear program. So, okay, so first of all, actually let xe be a variable for each edge. So the variables, they're not called x1 up to xn, they're just called xe for e and edge, but it's the same thing, right? And I want to maximize the sum of the xe's subject to, well, okay, so I want to encode the matching problem. So think of each edge of the graph. So each edge of the graph is assigned to a number. So in the end, we're going to have some constraint saying that xe's are all integers, right? So one way to think of a matching is you can think of assigning each edge to a value 0 or 1, right? So, and if you assign each edge to a value 0 or 1, what's the matching condition say? Well, it says that from any vertex, if I look at it, I look at the edges coming from it. So remember, matching, you're only allowed to use one of these edges in the matching. So that means that on every vertex, if I look at the edges containing it, their variables have to sum to at most 1, right? So if I look at the sum over all edges such that E contains V xe, that has to be at most 1 for each vertex V. So it looks like I've written just one constraint here, but this is actually, so I have this constraint for every single vertex. So you should think of this as listing out, size of V constraints. And I want to say that also, so I don't want to use negative numbers. So I want to say that xe has to be at least 0 for all edges. Sorry, this got a bit messy, but right. And okay, so if I'm saying that every edge has to have a value at least 0, and you have this constraint, then actually, if you think about it, every edge has to get a number either 0 or 1, because if any particular edge got 2, you would violate this constraint for both of its endpoints, right? So so what I claim is that this ILP exactly computes nu of G, which is, remember, that's the size of the biggest matching in G, right? And to see this, so if M is matching, then setting, so if I take these variables, if I just set xe to equal 0 if E is not in M, and 1 if E is in M, right? This satisfies the constraints. Yep.
What character?
Nu. So this is the size of the Greek letter nu. I mean, but this is. Sorry, you're saying so an integer linear program or a linear program, or?
Do you have to find the optimal assignment variables, or just select the value?
Oh, I see. Like you mean like what counts as being solved? I think the thing is it would be hard to find the optimum value without finding those. So technically, technically you need to find the optimum value, and you need to have some certificate of optimality, right? But and some certificate that is actually achieved. Technically, it doesn't have to be the assignment of the variables, technically, but it'll be hard for you to give me a different certificate that's not that. I mean, so technically you don't have to have that, but yeah. Okay, so if M is a matching, then we can, so if we have some matching, we can set the variables so that it satisfies the constraints, and the value of the, well, objective function for this choice of the variables will be just the size of M. So in particular, if we take M to be the biggest matching, then you'll assign the variables so that the value of the objective function will be new. But then, of course, in the other direction, so also for any choice of variables, choice of values for the variables, satisfying the constraints, right? We can then turn that into a matching by taking. So if I take the set M to be all the edges E such that x equals 1, this is going to be a matching, right? And again, the size of this matching is going to be equal to the value of the objective function. So yeah, I mean, if you think about it, it's kind of clear that this should give you, compute the value of the biggest matching, but these are the kind of details which, yeah, so it's a matching with cardinality. Right. So this kind of shows that this integer linear program would actually give you the size of the biggest matching, right? And then you could think, I mean, a lot of the things that we've done in this module, for example, looking at cliques or stable sets, right? You could write that as an integer linear program, finding the biggest clique, for example. One slightly trickier one is max flow min cut. Finding. So if I wanted to find the max flow in some sort of network, right? Well, actually, I mean, the trick is actually it's easier to write the min cut as an integer linear program than the max flow, and that'll give you the actual integer linear program. Anyway, so this is just an example, and this is going to come back in the next few lectures, like specifically this matching problem. Okay. Right, so ideally what we want to do is, kind of, like, so I mentioned at some point, so it's hard to prove, but so we didn't prove it, but I mentioned at some point that linear programs can be solved in polynomial time. Right, so ideally what we'd like to do using this integer programming thing is to sort of take a problem that we don't know how to solve, or even when we know how to solve, like matching problems, turn it into a linear program, and then use the fact that linear programs can be solved in polynomial time, right? Okay. So if you have an integer linear program, so there's this natural connection to. Okay, so let me just say, so given an integer linear program, so you always have this constraint that the variables are integers. If you remove that constraint, that gives you a linear program, which we call the LP relaxation. So the LP relaxation is the linear program obtained from removing the constraint that the variables are integers. So there's one kind of clear connection between the integer linear program and its LP relaxation, which is that in particular you have one sort of inequality. So the value of so think of this. So think of the linear program as a maximization problem. Of course, for a minimization problem, everything is similar. It's just the inequalities go the opposite way. is always at most the value of its LP relaxation. And this is sort of clear, right? Because the LP relaxation, it's optimizing over a bigger set of values because it has one less constraint. So the reason is because this is maximizing over a larger set of choices, let's say, for the variables. And if you maximize over a bigger set, obviously your maximum can only go up, right? So these are just sort of some definitions so far. Yeah, one thing is like it would be really great if this gives you at most, so you have an inequality one direction. It'd be really great if you knew that your integer linear program had value equal to the linear program or the LP relaxation, because like I said, so linear programs can be solved in polynomial time. So you would just be able to solve your integer linear program in polynomial time, right? And that's going to be a theme of the next few lectures. You know, under what conditions is it true that some integer linear program has the same value as its LP relaxation? Okay, so let me just say that generally, you know, these so generally, and I mean this should be kind of clear, but I'll give you an example. You know. So the value of an integer linear program is not equal to the value of its relaxation, LP relaxation. Right? You can even think of this matching thing. So let's say G is just the graph, you know, 3 vertices joined in a triangle, right? And I'll call this edge E1. This one E2, and this one E3, right? So if I was to write out this matching integer linear program, so the matching ILP will be, you want to maximize, so there's only 3 edges, so I'll just write xe1 plus xe2 plus xe3, right? Subject to, so what are my constraints? So the constraints, so for every vertex, I have the constraint that the edges containing that vertex have value at most 1. So for this vertex here, right, I have the constraint that the value on E1 plus E2 has to be at most 1. Now if I look at this vertex, I have that E1 plus E3 is at most 1. And if I look at this last vertex, E2 plus E3 is at most 1. And then I have I have non-negativity constraints. So all of these things have to be non-negative. And I have the constraint that they all have to be integers. Right? So imagine this line is below that line. Right, well, okay. I mean, this graph is small enough that we can just analyze it, right? So what's the biggest size of the biggest matching? It's 1, because, you know, I can take one of these edges, it doesn't really matter which one, by symmetry, and then I'm not allowed to take any more edges because it certainly wouldn't make a matching, right? So this has value. So this whole thing I wrote here has value 1. But if I look at its relaxation, so that's the exact same linear program, except I ignore this integer constraint. Well, so for the relaxation, it's valid if I setting all the variables equal to 1/2, for example, is feasible. So for the, right, because you can see that, so all the it satisfies the constraints, right? So everything is non-negative, and at each vertex, if I look at the edges containing that vertex, they sum to 1, right? You know, the value here and here sums to 1. 1/2 plus 1/2 is 1, and has value 3/2 because, well, 3 times 1/2, which is strictly greater than the value of the integer linear program. Right? So this gives an example showing that, you know, often you can't just go right to the, taking an LP relaxation, it gives you a different value. Okay. Any questions about that example? And it turns out there's a very good reason why, like, okay, so if we lived in a very friendly world, right? If I took an integer linear program and I just wrote its LP relaxation, you know, I would always be able to solve things that way. But there's a reason. I mean, we don't live in such a nice world. Remember, back in, I don't know, week 4 or 5 or something, I gave you all these things about hardness of, you know, where we don't have algorithms and things like that. And this, you know, integer linear programming problems turn out to be a hard problem. So it is NP complete to decide. So remember, when we talk about NP complete, it's always a decision problem. It has to be a yes or no question. But so it's NP complete to decide if a given integer linear program is feasible. Right. So if somebody gives you a general integer linear program and they just say, is there at least one feasible point, that's a hard problem. So in particular, if you want to find the optimum of an integer linear program, that's also going to be a hard problem. And maybe I won't give a completely formal proof of this, giving all the details, but let me give, or maybe I almost have time, but let me give you a sort of sketch. Right, so one way, so there's lots of different ways you can do it. One way is you can do a reduction from 3-SAT. Yeah, so I kind of expect that by now you've forgotten these things about reductions and 3-SAT and stuff like that. But basically what we want to do is take 3-SAT, so transform into this problem. Right? So you want the problem of checking whether some integer linear program is feasible. Right? And here's how the transformation basically works. So suppose you have some instance of 3-SAT. So I'm going to show just kind of one example of how you would take an instance of 3-SAT and turn it into a integer linear program constraints, set of constraints. But it should be clear that this sort of works in general. So suppose I take something like this. So let's say, I don't know, x1 or not x2 or x4. I don't know. I'm just kind of making things up. So okay. So that's a valid instance of 3-SAT, right? You have a bunch of clauses. So remember, this thing means or, right? This thing means and we think about assigning these variables to true or false. So you want to know if there's a way of assigning these things to true or false, such that this evaluates to true, right? And I want to turn this into some sort of linear program, or sorry, integer linear program. So think of xi equaling 1 as being true, you know, as that variable being true. 0 is false, right? And so if this thing is feasible, remember, so you want to assign the variable so that at least one of these 3 things is true, so that this evaluates to true, and at least one of these is true, so this evaluates to true, and at least one of these is true, right? So, but I can write that as, so if I say x1 plus x2 plus 1 minus x3 at least 1, so all my variables, I'm going to think of them as being either 0 or 1. So that's my sort of integer constraint, right? So if x1 plus x2 plus 1 minus x3 is at least 1, then I know that either this one was 1, or that one was 1, or that one was 0, which means the negation was true, right? So then my next constraint is x1 plus 1 minus x2 plus x4 is at least 1. And my last one is just x3 plus x4 is at least 1. And this is my integer constraint. So okay, this is not quite the same format that I was writing things in before, but of course, this is the same as writing that my xi's are at least 0, my xi's are at most 1, and my xi's are integers, right? Yeah.
Is it atoms?
Sorry, is it atoms? Oh, sorry, can you say the word again? Yeah. Oh, literals? Is that the word you? Yeah. So each of these are literals. Yeah. Here and here, I just called the variables the same thing, right? But I mean, it doesn't really matter, right? Okay, so this is just one example of how you would transform this. So I think it should be clear that this is satisfiable, meaning that there's something where it evaluates to true, if and only if these three inequalities are feasible, right? So, and in general, you could just, it's all the same to do this in complete generality, right? So we know that 3-sat is NP complete, and I just showed, I showed one example, but essentially you could show that any instance of 3-sat can be turned into this problem of deciding if an ILP is feasible, therefore that must be NP complete. Oh, well, it must be NP hard. Remember, we have to show that it's in NP, but that's easy because you can just say, so the certificate is just a value of each variable, and you can easily check the constraints in polynomial time, right? Yeah?
And normally your covariant problem you must use any real number, containing greater than or less than sign, as opposed to greater than or equal to or less than or equal to.
Yeah. Oh, sorry. Like, yeah. So you can always write it if you want to like write a. So if you have some less than or equal to signs and some greater than or equal to signs. Oh, do you mean strictly greater and strictly less, or you normally avoid that sort of thing in a linear program because you might not have. Okay, you could sort of do that if you change your max to like a sup or something, supremum, because you might not have a maximum, right? So usually we just write them with strict, or sorry, not non-strict inequalities, because then you actually have a maximum and a minimum and that sort of thing. But sometimes you do want to solve problems that have strict inequalities, but then you can just kind of write the strict one. I mean, you can transform all these problems into the Anyway, you can sort of do that, but it takes a bit of thinking. So generally, integer linear programs are quite hard, even though linear programs can be solved in polynomial time. Okay, so let me just, so we might finish a bit early. So I just want to give now one more example of a integer linear program, which is quite a popular one, and it's something slightly different than what we've seen so far. So this is called the Knapsack Problem. Okay, so the basic kind of setup is, suppose that you're, going on holiday or something, right? And you want to pack your bag, and so you want to, so each item that you have has some value. So let's say the ith item has value vi. So maybe the value, so if you're going on holiday, maybe the value is like something to do with how valuable it is on that trip. So if you're going to the beach, right, your snorkel might have high value or something like that. Your swimming shorts or swimming costume would certainly have high value. And each item also has some size. Right? Some things are obviously bigger than others. And you need to fit these things in, like the things that you take, you have to be able to fit it into your knapsack or suitcase or whatever. And naturally, you want to take kind of the highest value set of items that you possibly can, right? So you want to take, so let's say your knapsack or your suitcase or whatever has capacity, let's say K, right? Oh, so let's say the size of this thing is, I don't know, SI for the ith item. And so naturally you want to maximize the value of items you take. And obviously, like every item, you either take it or you don't. You can't take like 30% of an item, right? So these are kind of integer things rather than linear program. So the kind of integer linear program here now is maximize. So you want to maximize the sum of your I equals 1 to n vi xi. So xi is, let's say, yeah, so xi is 0 or 1. It's 0 if you don't take the item, and it's 1 if you do take the item. And you just have one constraint, right? Or, well, okay, apart from this constraint, I just have one size constraint that the stuff you take has to fit in the bag, right? Okay. So this is the knapsack problem. Yeah, so this is, I mean, it's a very, very simple type of integer linear program, right? It just has, so apart from this integer constraint, it has one linear constraint. Really, not very much to it. But it turns out, so this is not something I'll prove, but it's NP complete to decide whether the value of a knapsack problem is at least like, I don't know, t for some t. Right? So if you're given a decision problem where you're given a knapsack problem and you're given an integer or a real number t, it's NP complete to determine if you can actually get, if this value is actually at least t. This is quite a simple linear program or integer linear program, but even these things are NP complete. Okay, so let me just end by kind of setting up what we're going to do for the next couple of days, just sort of introducing some ideas, and then I'll basically kind of repeat some of them tomorrow. So So remember, so there's something we didn't prove about linear programs, but I mentioned it, that so if you take okay, so you have a linear program, right? So the set, so you're optimizing over the set of vectors where you have, so ax at most b. So remember, this is something called a polyhedron. And okay, so if you think about it, if you had a two-dimensional kind of picture, right, these things usually look like some sort of, right? Right, so you should think of this polyhedron as being some sort of, geometric shape. And so this is in 2 dimensions, but you can have these things in n dimensions, right? And I mentioned that the optimum value of any sort of linear objective function is attained at one of the corners. Right? So the maximum possible value will be at one of these points, right, for any linear program. So here's a very basic thing. So suppose you have an integer linear program and you take the LP relaxation, right? So we know that you're not going to get equality necessarily in their value, but suppose, so you have an integer linear program, and you know that all the corners of this polyhedron, well, so when you think about it as a linear program, are integer vectors. Right? So suppose you just somehow you know that. Well then, definitely, so then the value of the integer linear program will equal the value of the LP relaxation. Right? So this is just a basic thing because the linear program is optimized at one of the corners. All of those corners are feasible for the integer linear program. So one of them is best for the linear program, and it has to also be best for the integer linear program because, yeah. So this is like basic, but the kind of, so the sort of thing we're going to be looking at is kind of for which, matrices A and vectors B, can we be sure that the corners are integer vectors, right? And that's going to be the topic of the next 2 days. So if you do know that, if you do have some conditions on these things, so that you know that all the corners of this polytope or polyhedron are integer, then you can just take your integer linear program, write the LP relaxation, solve it in polynomial time, and that'll solve the integer linear programming problem, right? Okay. And in particular, we're going to see that there are some natural kind of problems, like for example, matching problems, where you do actually get, so the kind of the matrix you have there, you actually do get something which where you can prove that all the corners are going to be integers. Okay. Okay. So that's all for today.